Hello, I'm Joshua Freedman, Senior Analyst at Rapaport, and welcome to the latest episode of Rapaport's new LinkedIn Live series, GEMTalks, in which we speak with experts from the diamond industry about important topics affecting the sector. This episode of the Rapaport LinkedIn Live is brought to you by the GIA, the Gemological Institute of America, protecting consumers and supporting the global gem and jewelry trade since 1931 through research, education, and laboratory services. The natural diamond industry has put much time, effort, and money into differentiating its product from lab-grown diamonds. Yet many consumers are still unaware of the differences, and the message that often gets through is that mined and synthetic diamonds are the same except for the price. In this session, we will challenge that perception with the help of Dr. Ulrika F.S, Senior Manager of Diamond Research at the GIA. Dr. F.S joined the GIA's New York laboratory as a research scientist in 2011. She researches the defects of natural treated and laboratory-grown diamonds, with a particular focus on developing methods to identify and separate them. She also manages the GIA's CVD lab, which works on creating reproducible growth procedures for gem quality synthetic diamonds. Dr. F.S will talk with us about the physical differences between natural and lab-grown diamonds and how this helps tell a story to consumers. This is a vital topic for the continued existence of the diamond trade. Later on, she will answer your questions, so please post them throughout the session in the comments on this event. To begin, we will be treated to a presentation on this topic, so a big welcome to Dr. F.S.
Thank you very much. Let me just pull up my slides. Excellent. I hope everyone can see that. So thank you very much, Joshua and Rapaport, for giving me the opportunity to sort of give you a bit of a deeper insight into ways that we differentiate natural and laboratory grown diamonds, both in the sense of their stories, but also separating them based on their growth histories and how we're able to differentiate the materials in a laboratory setting, so how we can identify them. So obviously, in particular in the last 5 years, there has been enormous influx of laboratory-grown diamonds in the gem trade, and this has presented a certain series of industry challenges. They're widely available, they're highly visible in the press, and this has unfortunately led to a mixture of both highly informed but also misinformed clients and retailers. And this obviously leads to confusion and mistrust. Intentional and unintentional mixing of lab-grown diamonds can also occur. And really the most important thing is that they need to be differentiated. This is key. So today I'll be going through a series of different topics relating to natural and laboratory-grown diamonds. Firstly, we'll set up the baseline by defining what diamond is. Then we're going to discuss natural diamonds, how old they are, how they form, and also touch upon their rarity. Then we will go through laboratory-grown diamonds, separating the two main growth methods, the HPHD, or high-pressure, high-temperature method, and the CVD, or chemical vapor deposition grown method, the two main methods used for gem quality production. And then take a look at the evolution of lab-grown diamonds over the past few decades. And then finally, we're going to discuss how we separate natural and laboratory-grown diamonds, both within the lab, what you might be able to do yourselves using screening tools or even your standard microscope and tool, learning some of the limitations and the challenges, and then where to get more information. So firstly, let's define what diamond is. So diamond is just a very specific arrangement of carbon atoms, shown here in black, where each carbon atom is covalently bonded to 4 nearest neighboring atoms. This is exactly the same type of carbon atom that is present in graphite. The key distinction is their bonding. So for both laboratory-grown diamonds and natural diamonds, they have this bonding arrangement shown at the bottom, these 4 carbon atoms surrounding another one. Now let's touch upon natural diamonds and their story, their unique story. So natural diamonds, firstly, I really want to emphasize this because it's one of the key distinctions is they are old. They formed 90 million to 3.5 billion years ago. Now, to place that in form of reference, compare that to dinosaurs. When were they extinct? That was over 65 million years ago. Everyone thinks of dinosaurs as being old. How about looking further back, the age of the Earth? Earth is 4.56 billion years. So these diamonds have really been hanging around for a very, very long time. Natural diamonds are also the deepest gemstones. Unlike many of the other types of materials that we pride ourselves in wearing as jewelry, these are coming from extreme depths. They form deep within the earth by carbon-containing fluids and rocks at depths of between 150 and 200 kilometers for the vast majority of them. However, some of them can come from depths of over 700 kilometers in depth, super deep diamonds. So as a frame of reference, the deepest hole that humans have made, artificially made hole, is the Kola Super Deep Borehole, and that's about 12.2 kilometers deep. Everest, the highest mountain on Earth, is only about 8.8 kilometers high. So this is really, really extremely deep, and diamonds are really the only ways that we're able to study these great depths of the Earth, and therefore, obviously, geologists are extremely excited whenever we're able to study a diamond. Now, these diamonds coming from those depths, how were they brought up? They were brought up to the surface by ancient volcanic eruptions. So the last diamond-bearing kimberlite eruption that we had occurred 19 to 24 million years ago. See, those are truly ancient events. And again, the fact that these diamonds are able to be brought up through these explosive events and survive is really a testament to their resilience and adds to their exciting story. So if you know that you need to look for these sort of kimberlite pipes, this material that is diamond bearing, we need to look at where they might be in the earth. Are they everywhere? Well, these kimberlites are associated only with the oldest parts of the earth, known as cratons. Here in these diagrams, they're shown as sort of these brown and gray regions. Now, even if you find a craton that has a kimberlite in it, only about 3% of those kimberlites are going to contain diamonds. So that's one of the big challenges for diamond exploration. So natural diamonds are rare. Here we have an example of the Letseng mine in Lesotho, where it has a very, very low grade, only about 0.01 carats per ton. So if you have this human standing next to a 50-ton truck for scale, this particular truck might only contain 1 total carat of diamonds. So you need to extract quite a lot of material indeed in order to be able to find diamonds. And this grade is going to vary from mine to mine. This is Letseng, which is known for having a very low grade, but very valuable stones coming out of it, whereas most commercial mines average about 0.3 to 1 carat per ton. I.e., that means that this 50-ton truck could potentially contain about 15 to 50 carats of total weight of diamonds, but this is going to be mixed quality. And then out of those, only about 30% of the diamonds recovered are actually gem quality. Now, moving on to what if you want to have 1 carat D flawless diamond? In order to recover that, you might need to recover about 100,000 tons of ore. That's the equivalent of 2,000 trucks filled with ore. So this really, really emphasizes that finding diamonds is actually really quite difficult, and it is a rare occurrence. Now moving on to laboratory-grown diamonds. So laboratory-grown gem diamonds are produced in factories. They have the same composition and crystal structure, so they have the same bonding arrangement of carbon atoms as natural diamonds, and they have essentially the same physical, chemical, and optical properties of natural diamonds as well. However, they have a fundamentally different story. Now, when it comes to the naming, let's really sort of narrow down on that. In 2018, the FTC updated the jewelry guides in the United States. And the recommendations are that to ensure that things are very, very clear in the trade, that we use the terms such as laboratory grown, laboratory created, and manufacturer name created. The unqualified diamond can only be used to refer to natural mined diamonds. Now, the term synthetic, notably, is not prohibited, and it is commonly used outside of the United States. Now, moving on to the growth methods. For the main laboratory-grown diamond methods, we have about 20% of what we see at GIA is produced by the high-pressure, high-temperature method, where you're effectively going to be compressing and converting a source of carbon at very high temperatures and pressures, trying to mimic some of the natural diamond formation methods. And then the remaining, the 80%, is produced by the chemical vapor deposition method. And this is dramatically different. It's based on gas phase chemistry. And I like to think of it as just a very fancy microwave oven that's able to grow diamonds. But we'll look into these two methods in more detail now. So the HPHD grown diamonds use a HPHD press. Again, HPHD stands for high pressure, high temperature. And it's going to mimic some of the key conditions of natural diamond growth, but not the chemistry. The pressures that they apply are fixed at 5 to 6 gigapascals, temperatures up to about 1600 degrees Celsius, and depending on the quality and quantity of diamonds that you're trying to produce, it can be running between days to months. So here on the right, you have an example of a little cartoon showing the inside of this reactor. So you have a little diamond seed. In order to grow any type of diamond, you have to start with a little piece of diamond as a template. And then above that, they have a mixture of metals, the source of carbon. They heat it up. The carbon dissolves into the melting metal, recrystallizes this new diamond onto the seed, and that gives you your HPHD diamond. Meanwhile, the CVD grown diamonds, the chemical vapor deposition grown diamonds, use a gaseous carbon source and plenty of hydrogen. And you can see here on the right, you have an example of what a cartoon of a CVD reactor. You have a series of seeds, again, pieces of diamond that you have to use for growth. And then above that, you have a plasma. You apply microwaves to activate a plasma from all these different gaseous constituents, and then atom by atom, layer by layer, you'll be able to grow new diamond material. And you can see here on the bottom right, you have a CVD diamond in growth. In fact, this was taken at the GIA labs, the CVD growth lab. So you have your CVD diamond, and above that, you have that plasma of the gaseous species. And again, depending on the quality, the color, the quantity of samples you're going to be growing, it can range from days to months. Now, in the past couple of decades, there's been a huge evolution in the quality and the sizes and the quantity of laboratory-grown diamonds. So here we have an example of the CVD-grown diamonds. And back in the early 2000s, most of the material was really brown, small, not necessarily the most valuable within the gem trade. But as they have perfected their growth procedures, they have also introduced post-growth treatments. We have seen a huge increase in both the size and the quality, with the largest ones reaching now about 75 carats inside, faceted. And this diagram here, I just want to highlight the fact that GIA publishes materials in a range of different sources, including Gems and Gemology, and this is from a big review article that we released this past summer. And this is really just tracking the evolution of laboratory-grown diamonds as they're coming through at the GIA lab. So you can see here very dramatically that the sizes for the CVD grown and the HPHD grown have been increasing dramatically over the years. Nowadays, for CVD, most of the samples that we see are larger than 3 carats in size, whereas those produced by HPHD are greater than 2 carats in size. So that obviously within the gem trade is a significant size. So the key thing is going to be the distinction between natural and laboratory grown diamonds in order to maintain what I like to think of as the 5th C, the confidence. As long as they are sold with full disclosure of their man-made origin, they do provide consumers with options. But the key thing is that we need to ensure that there is education. We have to have grading reports that clearly differentiate between these goods. And also GIA supports the trade by producing screening equipment that is easily accessible to, again, create that confidence in what it is that you're looking at. Now, in the past, visual clues would have been very, very easy. You can potentially use a microscope to differentiate the growth history because it could potentially incorporate certain inclusions that you could use that you could identify by using a microscope. And this was certainly the case for the first materials. However, now, in particular, with the higher clarity goods that we're observing, you often can't distinguish them by eye. Let's say you had a rough crystal in front of you. If it was a rough HPHD grown, it will have a cube octahedral growth morphology, so sort of a blocky nature to it. If you have your rough CVD grown diamond, you're going to have a cube, potentially with polycrystalline edges, It doesn't look particularly appealing here, but it could be treated to decolorize it. And then you could have a rough natural diamond, which has a very characteristic, could potentially have a very characteristic octahedral growth pattern. So these could be visually identified, but if you cut the stone, you've lost all of that information. So what do we have? What clues do we have available to us? Well, one of the clues that we can look for are the inclusions. So natural diamond crystals, as they're growing, can trap non-diamond minerals. This is extremely valuable for the scientific community, as it's one of the only ways for scientists to access some of these materials and learn about the evolution of the Earth. It is a snapshot of the composition of the deep Earth at that time. And by analyzing these inclusions, we can find information about where the diamond might have formed, as in the depth of the diamond, and also its age. So all those numbers that I was giving you before about the age of natural diamonds, that's because people have been analyzing these inclusions. So these inclusions are really, really quite valuable to us. Natural inclusions, there's a range of different minerals that can be trapped. One of the most common ones is going to be olivine, shown here on the left, which is going to be colorless or potentially have a little bit of a sort of light green color to it. But you can have a range of different types of inclusions here showing different colors. Now, if we move to the laboratory-grown diamonds, the HPHD-grown diamonds, in particular the older products, were really susceptible to trapping some of the metal flux that they were grown in. So little chunks of metal that are trapped within. Oftentimes, these inclusions have rod shapes, and they can have this metallic luster to them. Additionally, because they are metallic in nature, they are magnetic. So if you were to have, say, a parcel of lots of melee diamonds with lots of inclusions, and you passed over it with a very strong rare earth magnet, you might actually find that you're able to pick up these stones due to the magnetic nature of the metallic inclusions within them. And this is something that can be particularly helpful for those small stone screening. For the CVD grown, though, it gets a little bit more complicated. You see, most of the material that's trapped in there is essentially just carbon that didn't quite bond properly. So you have essentially graphitic material or non-diamond carbon materials inside. Sometimes if these diamonds have been HPHD processed to decolorize them, you might get a little bit of a stress halo surrounding one of these. But really, these inclusions are very similar to what you might potentially see in a natural diamond as well, so they're not particularly diagnostic. Now, what if you look at your diamond between cross polarizers and look at the strain patterns, the birefringence patterns? For natural diamonds, they have had this sort of very stressed environment down there in the depths of formation and in their residence. So typically you're going to observe different types of strain patterns, oftentimes with very strong, colorful colors, but potentially some more subdued tatami or cross-shaped patterns. If we look at the CVD grown, because there has been such a change over the years, you might actually see patterns that are really quite similar to what you observe in natural diamonds, so not very helpful. But the reason I bring this up is that for the HPHD grown, because they are grown with very, very even pressures from all different directions, they actually have extremely low, unusually low strain and stress in them, which gives you this sort of very clear clear view through the stone without any sort of clear strain patterns, except directly adjacent to inclusions. So this in itself can actually be very good warning sign that the stone needs to be looked at more carefully. Now, moving on from those things, what do we have to rely on? Well, I know we like to think of diamond as being perfect, but the diamond crystal is not perfect. It has atomic level lattice irregularities called color centers or defects. These can be missing atoms or impurities within the structure. And this is something that is present in all diamonds, whether natural or laboratory grown. But these are useful to us. These are really what give us the stone their personality. These give us a snapshot of what's in there. So by considering using a range of different techniques, the presence, absence, relative concentrations, and distributions of the different types of defects that are present within a diamond, we are able to unravel its history. So these impurities and atomic level defects are going to change the properties of the material. They will change the way that the diamond interacts with the light. It can lead to absorption. If you have sufficient amount of these defects or impurities, you will have a change in the color. And this is why, even though we call it defects or color centers, we have to keep in mind that these are not a bad thing. For instance, beautiful blue diamonds like the Hope Diamond, they're blue because of the presence of boron in the material. So these are not a negative thing at all. So they affect the way that the light is absorbed through the stone, and it also affects the emission of light. So these defects are going to absorb some of the light and then potentially emit light, producing fluorescence. So these are ways that we're able to identify their presence. So within a well-equipped gem lab, we're going to have an advanced identification toolbox that includes UV fluorescence, phosphorescence techniques, photoluminescence spectroscopy and mapping, again, looking at the emission of light from these diamonds, FTIR and UV-vis absorption spectroscopy. So these are looking at the way that light is absorbed through the stone. So the one that I'm going to focus on today is just the UV fluorescence and phosphorescence. Now, these defect distributions, when a diamond is growing, it's going to experience a whole slew of different events through its growth history. In the same way that if you have a tree, it might experience disease or have cyclical changes in the climate. And all of this is going to create essentially a series of growth rings in its trunks. Diamonds have the same thing. They have their own fingerprint inside. And these defect distributions are going to be reflecting changes in the growth, the deformation, or even treatment. So here we have our natural diamond octahedron rough crystal. If we were to slice through its belly here, we would see essentially a series of growth rings. These rings for the vast majority of diamonds are going to be octahedral, which gives you a sort of square-shaped pattern in the center, but there can be a range of different, very clearly natural patterns with certain, that with practice you could recognize. So here you have an example of a natural diamond. In fact, these are really acting as fingerprints. These are two separate diamonds that were submitted to GIA around the same time, and we were able to match these patterns and actually say that these came from the same rough. So they are truly, truly intrinsic to the stone. Natural diamond patterns, depending on the types of impurities that are present. So whether it's a type 1 diamond with plenty of nitrogen, or even a high purity type 2 diamond, you will have different characteristic natural patterns. In fact, for the type 2 diamonds, which is the diamond type that we're most interested in when it comes to distinguishing with laboratory-grown diamonds, you would oftentimes see this sort of mosaic polygonized dislocation network. So it almost looks like cotton wool going through the stone. And this has to do with the way that the diamond has been formed. If you then move to laboratory-grown diamonds, for instance, those produced by HPHD growth, because of the way that they're growing, the incorporation of defects is going to be influenced. So for instance, in this example here, you have your diamond seed at the bottom, and as this crystal was growing, along different directions, different defects preferred going in. So in the 111 octahedral phase, nitrogen, which can give you yellow color, loves going in. So that section is going to have more nitrogen in it. And if you were to slice through it, you're going to have what's known as a Maltese or cuboctahedral pattern. So you have a square with a cross shape going through it. Again, very distinctive to what's seen in natural diamonds. And this can be observed in fancy colored diamonds through color zonation. So again, these impurities, these defects are what's causing the color. So higher concentrations go into certain growth sectors, and we can see that through color zonation, but even through fluorescence techniques where we illuminate the sample with UV light. In a fancy colored HPHD grown diamonds, you might be able to see that distribution even using a standard gem lamp with a shortwave UV. Or alternatively, you can use deep UV from an instrument such as the Diamond View, where the wavelength is less than 225 nanometers, and that's going to create a pattern that can be seen even in high purity type 2 HPHD grown stones. And in particular, these UV light sources are also able to induce phosphorescence, where the sample continues to glow even after you remove the UV. Now, phosphorescence is something that is extremely rare in natural diamonds, so being able to observe this can be a good warning sign that the diamond needs to be looked at more carefully. For the CVD grown diamonds, this is proceeding by layer growth, and it's going to create these ripples, these terraces and risers as it's growing. And again, the incorporation is going to vary between those risers and terraces, and it's going to create a very distinct set of patterns. So these striations, as they're known, which are these tightly spaced lines that are diagonal. And then if there are any interruptions during growth, you might also have a huge change in the impurity incorporation, creating these layered structures that by eye you might not be able to see, but by using fluorescence imaging, they can be clearly revealed. And these, again, if you were to look at this and you have the experience of having looked at a lot of natural diamonds, you would immediately say this is a lab-grown diamond. So this is very conclusive. Now, obviously, this is a very high-tech instrument where people have to have a lot of interpretation, the ability to interpret, and a lot of experience. But we also want to make sure that there are instruments that are available for the trade for screening. So using the same diamond fluorescence, so the emission of light when illuminated by UV, we're able to collect data on it and still separate natural and treated diamonds and give you an automatic result. So GIA developed the ID100 system where you illuminate the sample using a probe, and then it automatically collects the light, and within a couple of seconds you get a pass, meaning that it's a natural diamond, or refer, meaning that it's a stone that needs to be looked at more carefully using other techniques. And this is something that's extremely simple. No one needs to do any interpretation because the machine does it for you. So GIA's mission, as Joshua already introduced earlier today, is to ensure the public trust in gems and jewelry by upholding the highest standards of integrity, academic, science, and professionalism through education, research, laboratory services, and instrument development, such as the ID100. If you want to learn more, we are very, very keen to give you the information through several different avenues. So we have the Gems and Gemology journal, which is freely available online. And then again, I want to highlight that summer 2024 issue where we have a article that's reviewing the sort of update on the identification and the products of lab-grown diamonds that are coming through at GIA. And then we also publish a lot. The research team here publishes a lot elsewhere as well. So we have a publication archive. We have a gemological library, and we have publications, for instance, in this big volume here that was done with the Mineralogical Society of America and the Geochemical Society. It reviews really everything there is to know about both natural and laboratory grown diamonds. So if you want to do an in-depth dive, there's a lot of information there. And with that, I'd like to thank again Rapaport for giving me the opportunity to speak about laboratory-grown diamonds and natural diamonds, and I'm open for questions. Thank you.
Thank you very much, Dr. Dana Johansson, for that presentation. Just a reminder to everyone that you can post your questions in the comments, and we'll answer as many of them as possible. The comments on this LinkedIn event post. First, I had a few of my own questions. I actually wanted to ask, we mentioned in the introduction that you manage the GIA CVD lab. Could you tell us a little bit about what that is and what it does?
Of course. So GIA, as I've mentioned before, conducts a lot of research on both natural and laboratory grown diamonds. In fact, GIA started doing research when the first lab-grown diamonds came out in the 50s, before they were even in the gem trade. And this is partly because lab-grown diamonds are a gateway to understand defects in general in diamonds. So GIA has the CVD growth lab specifically to produce materials that are useful for research purposes, to understand, say, the origin of brown color in diamond, to tailor material that can be used for treatment to change a diamond's appearance, and also because it allows us to get a deeper understanding as to how the CVD growth is progressing in the industry as well. So it gives us that template for understanding their materials and their challenges as well.
Right.
And these materials are purely for research purposes. We are not producing any type of gemstones that are out for the trade or anything like that. This is purely fundamental research.
You'd have a good brand if you did, though. Also, a few things that came up in that presentation. You went through a few of the sort of diagnostic tests that you could do to identify if a diamond is natural CVD or HVHD. Which of those are sort of certain tests? Which of them give you certainty that it's lab grown, and which of them are just good indicators?
So most of the screening equipment, both ours and from others, are able to identify, so actively identify natural diamonds. So they're looking for natural diamond signatures. So if a diamond is passed or called natural, then you can be very certain about its origin. If it's referred, it means that there is an overlap in some of the features or that there's not enough to see. So as you've heard, the quality of these lab-grown diamonds has been improving so much that there's not necessarily much to signify it. And those will then be flagged and need to go elsewhere for further testing. And this is where it might be that you look at it between, say, if you have a diamond that refers, and if it was an HPHD diamond, you might be able to identify it by then throwing it into your microscope with cross polarizers and seeing that there's no strain in the material, or by looking at the inclusions and recognizing that they're metallic in nature, or looking at the phosphorescence. So if it phosphoresces, if you combine all those things, it's usually a range of different techniques that have to be combined to reach that conclusion.
Right. Um, and you mentioned magnetism with HPHT. How good is that as a test?
Well, so it depends on the clarity of the stone, obviously. So if
Right.
it's a high clarity stone, it won't be magnetic because it's not the diamond itself that's magnetic. It's the metallic inclusions side. One of the key metals that they use is iron. So essentially, you have chunks of iron inside of your stone. There are extremely, extremely rare natural diamonds that can also have metallic inclusions in there. So again, this is where you would have to look at the inclusion and make an evaluation as to whether it's natural looking or HPHT looking. So again, it's where you have to throw in all those tools. But it is certainly for melee-sized goods that are poorer quality, so more included materials. You can literally just grab your magnet above it and it will pick them up. So it can be very powerful. But it's just sort of one of the tools in your arsenal.
Right. We've got a question in about the name of lab-grown diamonds.
Mm-hmm.
The person who asked the question actually asked if there was another name that lab-grown diamonds could be called that doesn't mention diamonds. Um, that's quite an interesting suggestion. But maybe before we get to that, what do you think about the terms synthetic diamonds, lab-grown diamonds? Which of those do you think is the most gemologically accurate?
Well, the one that leads to the least confusion with ultimately the consumer is going to be the full term, so laboratory grown. It makes it clear that it was made by humans or man-made. The term synthetic, interestingly, can cause confusion. So unfortunately, in the past, it was used sort of bandied in a way to almost say that it was fake or that it was a material that was a simulant. So people confuse the term synthetic and simulant very easily if they're not in the trade. So although synthetic is something that is used for man-made gemstones that are not diamond, and that's accepted in the trade and sort of people understand that, within the diamond field, consumers oftentimes get confused by synthetic, meaning that it's not actually diamond. And chemically speaking, this is diamond. So I scientifically, like if I'm writing a paper on diamond, I might use the term synthetic because of the audience. But if we're talking about the general trade audience, laboratory grown is the one that's going to cause the least confusion.
Mm. Um, and if a friend were to ask you, is this diamond real? And it was a lab-grown diamond, how would you respond?
Again, it's terminology. I mean, real is such to some extent a loaded word because it is a diamond. It is a diamond material. And I just clarify that it's made by humans. I can even go into the details of how it was grown versus how a natural diamond was grown. They are both diamond materials, but they present very different stories of formation. And because of that, the story is a lot of what makes people interested in diamonds as gemstones as well. So that story is oftentimes the selling point of the material.
Right. Um, you mentioned something interesting about the depth at which diamonds formed.
Mm-hmm.
I think you said they're the deepest forming gemstone.
Yes.
I was wondering what's the next deepest forming gemstone after diamonds?
Ooh, that's That's actually a great question. Unfortunately, I am very much a diamond-centric
Okay.
person, so I wouldn't be able to comment
Okay.
on the
No
depth.
problem.
But I do know that the vast majority of colored stones are produced in the crust, which is partly why they have these inclusions inside of them that can help sort of guide as to where in the world they might have formed. So there's a lot more information in those stones because there's differences in the crust, whereas diamonds just form really, really deep, where everything's a little bit more even.
Okay. Also, I was curious about the issue of grade and quality of the grade of ore and then the quality of the diamonds in it. What are the geological factors that affect the grade of a kimberlite ore and then affect the quality of the diamonds that it produces?
Sorry, could you repeat that,
Yeah.
please?
What are the geological factors that influence the grade of ore?
Oh, there's so much that goes to it. It's not specific to the kimberlite pipe. Think of the kimberlite as that's just the conveyor belt that brings the material up. So the way that the diamond formed is at those extreme depths. There aren't, although there are a few mines that are known for producing very high purity clipper type 2 diamonds, you will find similar diamonds across the world, generally speaking. And it's the incorporation of, say, nitrogen that's present in the fluids as it's forming, the way that it's been heated, the duration of the heat, the pressure, all of that is going to create its own unique combination of defects and unique colors and grading properties. So each natural stone is truly unique. They have had their own experiences in the earth.
Right. And back to the question of the name for lab grown diamonds. Someone did point out that in France only synthetic is allowed to be used. I was
Yep.
wondering if you had any thoughts on that decision.
I mean, as long as it's clear to the consumer, the synthetic is an accurate term.
Right.
It's just we follow the guidelines set by the FTC in the United States, and we use
Right.
that terminology ourselves.
Okay. I've got a question here about another diamond screener. I don't think you would. I'm not sure that's something you'd want to answer. Um, and someone's asking what's the future resale value for lab grown diamonds, which is natural. But I think that's maybe a slightly different topic from this.
Yes, I think that's more something that Rapaport would be able to comment
Yeah,
on. We are unbiased. We just
yes,
characterize the material, then it's up to the market to set the
yeah,
value.
yeah. I was interested what you said about CVD diamonds with visible interruptions.
Mhm.
Does that still count as a single crystal diamond?
It does, because it is bonded throughout. So it is still a single crystal diamond.
So what exactly happens when the when the growth is interrupted?
So when they oftentimes growing a very thick material, it requires that they have to be able to maintain the conditions for extended periods of time. And technically that's really challenging. So some people have the approach that they grow and then they take it out, they cut off that polycrystalline material on the edges, and then they continue growing on that. As you do your startup procedure, you're not necessarily going to have exactly the same conditions that you had before. And as soon as you change the conditions slightly, that's going to create an interface. And even if you were growing a single crystal throughout, just one single uninterrupted growth, any changes in your conditions, be it the flow of the gas or the temperature, is going to change the incorporation of the impurities in the material as well. So we can see that.
Right. And what is the most important if you had to, to speak to a retailer about how they should communicate to consumers, what would you tell them is the most important difference between natural and lab grown diamonds?
The story, the formation, the age, the fact that the natural diamonds are a finite resource that's extremely challenging to access, the history behind it, and the sort of the allure of the story. Whereas the natural diamonds are the laboratory grown diamonds are technically really interesting, but they can be mass produced. So it's a different type of material in that sense. The story is dramatically different. It's cool that people are able to make it. It does mean that there's the possibility to tailor the material to the customer's needs and maybe create some interesting designs based on that. But it is intrinsically something that can just be produced at will.
Right. We got a good question came in here. In the future, do you think lab-grown diamonds can develop to be no phosphorescence and fluorescence and harder to distinguish from natural diamonds?
It is possible to develop that, whether it's commercially viable, especially for the sizes necessary to be sort of within the gem trade. It is possible, certainly, to produce those, but then it reaches the point where it's almost like they have too little in them, so they become noticeable because of that. They're almost like they're too high purity compared to the vast majority of natural diamonds.
Right.
So the fundamentally the way that they grew is still different. And even if you don't have any types of impurities within the material, there are still going to be features that we can observe to separate them.
Okay. I had a question here, which we did in fact cover this in an entire LinkedIn Live before. I think that was with Dr. Wang. But how does the ID GIA device work?
The ID 100?
Yes, yes.
Or the match ID?
I assume
I
this
just
is
realized we have two IDs.
I assume this is referring to the match ID.
The match ID. Okay, so the match ID is essentially any diamond that comes into GI that gets inscribed. We now record an image of the inscription. So we inscribe the report number, for instance. And we have all of this stored in a cloud so that with a match ID, you're able to take an image of your inscription and it communicates with our cloud, and then it will tell you whether it is indeed the same stone, because the faceting arrangement combined with the way that the inscription was made is unique to that stone. So even if someone were to inscribe that same report number on a different stone, it would be able to recognize that and say it's not a match.
Right, and this is another question that we've also done an entire LinkedIn Live on, but it's still an interesting question. And we could probably spend another 45 minutes talking about it. But the natural diamonds from different parts of the world have different fingerprints.
They do not. I know that this is a bit of a controversial subject, and I know that the trade, and honestly, all scientists would love it if there was something for that. But the thing is that the conditions that the diamonds grow in at those depths are actually geologically very similar across the world. So because of that, there's nothing unique to that locality. By the time it comes up to the surface, I mean, they grew billions and billions of years ago. Unlike, say, natural colored stones, they have that information from the crust, whereas there is much more variability from continent to continent or mine to mine. So because of that, they trap materials that can help separate them. So unfortunately, nothing likes to go into the carbon of the diamond. There's very little in there to look at. So the trace element concentrations are just too low to separate.
Okay. I've been corrected. The question before about the ID was about the device that you showed during this presentation.
Oh, the ID 100.
Right. Yep. How does that work? That was the question.
Okay, sure. So what happens is it shines UV light through the probe, through this little arm. So you have your little box that has a spectrometer in it and has all the analysis software and a little computer inside, and then a little probe that you use to sort of point at the stone, whether it's mounted, loose, rough, or polished. It illuminates the stone with UV light. The characteristic defects that are present inside of the stone will then emit light. They will fluoresce. And this will happen even in diamonds that on a grading report says that they are inert, that they do not fluoresce. This is so sensitive that it's able to pick that weak signal. It creates a graph that has a unique fingerprint to the fluorescence of that diamond. And then based on what's present in that, we're able to say whether it's natural, or in the absence of a specific feature, we're able to say that it's referred and needs to be tested further. It's collecting a spectrum. So unlike techniques that are based on just imaging where it's looking at it, it's actually collecting a very characteristic fingerprint of the fluorescence pattern.
Okay. Interesting question here. How do we know if there are any long-term health effects of lab-grown diamonds? Have there been any studies on that?
I don't believe there have been. I mean, the thing with diamond in general, it's just carbon, so your body doesn't really reject it. So there's in fact a lot of biological medical applications that use diamonds. So whether it's as natural or lab grown, the diamond shouldn't be affecting your health in any way.
So I just wanted to
Okay.
thank you, Dr. Hannah Johansson, for joining us today. I think
Thank you very much.
we'll go away with a much better idea of how natural and lab grown diamonds differ, and how particularly retailers can benefit from this knowledge. I certainly learned a lot. And if anyone has any further questions, don't hesitate to post them on this
Mhm.
on the post for this LinkedIn event. And thank you to everyone for participating and sending in your questions.